Hello everyone, welcome to today's class, Organic Spectroscopic Analysis. In the previous class, we have learned the NMR spectroscopy for hydrogen. Now we are going to learn NMR for carbons in this lecture. Like hydrogen 1, carbon-13 also has the 1/2 spin number and also shows the NMR effect. Carbon-13 is extremely useful for organic molecules. The signal is given for every type of carbon in a molecule. To achieve detectable carbon-13 NMR signals, we need concentrated samples of high purity, higher number of scans, and remove hydrogen couplings. NMR carbon-13 spectrum have a broad range and give signals to carbon atoms not connected to hydrogens. NMR carbon-13 is not quantitative, and it tells you the number of different carbons and the chemical type of carbons. However, there are two major problems with carbon NMR. There are only 1% of naturally occurring carbon-13 atoms. Carbon-13 has a much weaker magnetic moment. Each carbon-13 nucleus is about 6 times less sensitive in showing the NMR effect. So effectively, it's 6,000 times harder to observe carbon-13 than hydrogen-1. Decoupling simplifies the spectrum, one line per carbon type, focuses signal intensity for each carbon in one peak, therefore greatly improves signal-to-noise ratio. But wouldn't that coupling information be useful? Yes, it would. This is especially true when we will only look at those exceptionally large one-bond hydrogen-carbon coupling constants. A quick look at those will enable you to easily tell whether a carbon-13 signal is a methyl group or methylene group or non-protonated carbon. Fortunately, we have several sneaky ways of getting that information. Off-resonance decoupling, and DEPT, distortionless enhancement of polarization transfer. This is the proton decoupled carbon-13 NMR spectrum of 2-butanol. Every carbon has a single signal. There's one disadvantage of using a broadband decoupled spectrum. Integration of broadband decoupled carbon-13 NMR spectrum doesn't work because in radiating the nearby hydrogen masses with the signal intensities in other, less quantifiable ways. Generally, intensity goes methyl is larger than methylene and CH and much bigger than carbon. In addition, information is being lost by doing this, such as how many hydrogens are attached to each carbon. In off-resonance decoupling, the one-bond carbon-hydrogen couplings are retained. So the signal for particular carbon is given by the number of attached hydrogen in accord with N+ rule. So for example, a methyl shows as a quartet and the methylene as a triplet. This spectrum is the hydrogen-coupled carbon-13 NMR spectrum of 2-butanol. For off-resonance decoupling, only the one-bond coupling retained. DEPT represents distortionless enhancement of polarization transfer. In a DEPT experiment, a sequence of pulses with various delay times are used to create the DEPT spectra, while the methyl and CH peaks appear as normal and methylene peaks appear inverted. Quaternary carbon are not usually seen. This way, the number of hydrogen attached to carbon can usually be deduced. In DEPT 45, all signals will be positive, except the fully substituted carbons. In DEPT 90, only signals of CH groups will show. In DEPT 135, signals from methylene will be negative, while CH and the methyl group will be positive. So in this lecture, we have learned about the carbon-13 NMR spectroscopy. Hope you like it. Thank you for watching.